Let's take a look. We need to learn that one-dimensional motion with constant acceleration first, because that is a very simple case. So we can have something like position versus time. When we have position versus time, we can have curve like that. This only means that at any point we can find that position as x and time as t. Position at x, time as t. If we want to get instantaneous velocity at this particular point, then we need to find the slope of that tangential line. So once we find instantaneous velocity for every t moment, then we can start to draw. So what we do is, you see, initially is high, then start to get flat and zero. So initially is high, and then start to get zero. So initially is high, and then start to get zero, drop to zero, for example, and then start to change to the negative direction. Slope is negative. See here, slope is negative, and then that means the velocity is negative. It goes to negative region, for example, something like that. Okay, so we can have, let's say, make a smooth transaction, something like that. So a velocity versus time graph give us opportunity to get any moment, say what is v versus t at any moment. We can find that. Once we have a v versus t graph, we can find the instantaneous acceleration by using the same concept. For example, if this graph continues, and we can make it, for example, we can make it like that. And if we want to get the acceleration for this point, when v versus t, if you want to get acceleration, that is the slope of that tangential line. So we can find acceleration at this point. It's negative. So for this t moment, the a value is negative. So somewhere here, because that's positive direction. So it is very interesting to see that from a v versus t graph, we can actually find information. I should say, from x versus t, we can find information of v versus t. And then later from v versus t, we can find information from a versus t. Mathematically, that is also true. Let's take a look. Definition of instantaneous velocity is dx dt. And definition of instantaneous acceleration is dv dt. So let's start from the second equation. This is second equation, this is the first equation. And second equation gives dv equals to a dt. If we want to do integral, we just do that. Time is 0 to t. Initial time moment count is 0. Then your v is from v initial to v final. So the result of this integral really depends on your a. Now if we say constant acceleration, that means a is constant. Now we have to be very careful. When acceleration is constant, which means not only the magnitude, but also the direction, because acceleration is a vector. A vector has a magnitude and direction. Only when both magnitude and direction are constant, and we say that vector is constant. So we have to be very careful about that. So if acceleration is constant, we can have this a out of the sum integral, and we have dt. Then the life will be very easy, because if you take a look at that, dv integral will be v from v initial to v final, and dt integral will be dt. So a is a constant, dt integral will be t minus 0. So this will give us v final minus v initial at the left, and the right is a of t. If we rearrange it, most of the time we like to rearrange it in a way of, say, v final equals to v initial plus at. This is a very important equation, This tells us that if we know the constant acceleration, we know the initial velocity, then you give me a time interval, I can tell you what is the final velocity. So, which means you have information about A versus T, I can produce a V versus T. Then, how can we, from V versus T goes to X versus T? Yes, we can do that. Because we have this V equal to dx dt. This means dx equals to V dt. This V is the V at any time moment. It could be this any time moment. V is V final. So we plug in that. So V final is this V. That is our V initial plus AT. Have a dt. So if we want to do the integral, we just do this and that. Now, if the acceleration is constant, what we have is our left side will be, or dx, from x initial to x final. So left side will be x final minus x initial, or we name it delta x. That's left side. The right side, V initial is a constant, and dt. So the right side actually is this, V of initial of dt. The second term, A is a constant, so A out. We have t dt. For the dt, it is from 0 to t, 0 to t. So what are we going to have? Let's take a look. What are we going to have is, let's start here again. That is dx equals to v dt. Since this v is v at any time, we plug in that any time. V is v initial plus of a t. That is dt. And that will break as two terms. That is v initial of dt plus at of dt. If we want to do integral, then we just simply add the sign of here, here, and here. The result comes out as delta x equals to v initial, because that's constant. For dt, it's 0 to t. So it's t final minus the initial. Since acceleration is constant, a comes out. Now a comes out. T dt integral, that comes out of 1/2 t squared. And from what? For t 0 to t, so that's 0 to t. So if we reorganize that, we will get our first term is v initial t, second term plus 1/2 of a t squared. We get a very important equation now. That is change of position, which is the left side, equals to initial velocity times the time. That's this term, plus 1/2 of a t squared. And that is the second equation we reached. I want to point out a couple of things. Number one, delta x is change of position, I always say displacement. So it's a vector. That's why we have arrow. See that? Initial velocity, since the velocity, that's a vector. Acceleration, that's a vector. So we have three vectors. Vector, vector, vector. Second, I want to point out the units. Within equation, every single term must have the same units. See, delta x change of position is in meter. And the v initial is meter per second, then time, the time is second, then second cancels, still meter. And this term, acceleration, remember, is meter per second square, and the time is second of square. So second square cancels, we still have meter. So every single term is meter. We have the same units. Now, if I list equation 1, which is v final, equals to v initial plus at. The second equation we get is delta x equals to v initial of t plus 1/2 of at squared. That's two equations. If we combine these two to eliminate t, how do we do that? From this one, t equals to v final minus v initial divided by a. If we plug in this t right here, right there, guess what? We get a third equation, which will be v final square minus v initial square equals to 2a delta x. This is a very useful equation because this equation has no time. It says that if you know the initial velocity, you know the acceleration, so either way, if you give me the change of position, I tell you what's final velocity. If you give me the final velocity, I tell you change of position. So we have total of 3 equations that we can apply to different cases. That this deal with acceleration, initial velocity, final velocity. That deal with acceleration, initial velocity, time, and change of position. And this one, time is not involved. I would like to show you a couple of examples that we can learn how to use these 3 equations. Example 1. Let's say we have a car. VC1 is V car 1 is 25 meters per second. VC2 initial equal to 0. That means the second car initially is at rest and with an acceleration. What does that mean? For example, we have a car right here. This is a car. Let's name car 2. So it is at rest. At rest means that V car 2 of initial equal to 0. Initial is at rest. Then what happened is, let's assume this is the origin of x-axis and the positive to the right, it's in meter. And then there's a car called car 1, for example. Then let's draw a car. That's car 1. Car 1 simply drive this way with a constant velocity. Velocity means, well, to the right, positive, at 25 meters per second. So we say V car 1 equals to 25 meters per second. It's constant speed. Okay. So when car 1 pass position of x equal to 0, and the car 2 say, wait a minute, this is my friend. I need to catch him. So how does he do that? He has to accelerate. So his car allows him to accelerate at 5.0 meters per second squared. What does that mean? That means every 1 second, this car will increase speed by 5 meters per second. So the question is, when and where on the x-axis that car 2 will be able to catch car 1. Now, catch, what does that mean? That means they have to be at the same physical location. Let's assume both cars are just 2 points. We don't worry about the size. So what we're looking for is x of a, I should say x of 1 equals x of 2. Because car 1's position equals car 2 position, then car 2 catches car 1. So let's take a look. Now, car 1 travel at constant speed. So we say, okay, when it's going to catch 2 is going to catch 1, we say t seconds later. We don't know when, which is t seconds later. So for t seconds, this car 1 is going to travel at 25 meters per second for t second. We start t equal to 0 right here. So t seconds keep 25 meters per second. That's where the car 1 is. So 25, it's the speed, constant speed, or I should say velocity this time. Time to time, that's the position. Then, what's the position? How do we describe position for car 2? Well, we just learned. If we have initial velocity, acceleration, and time involved, isn't that true? There's an equation about delta x equals to of v initial t plus 1/2 at squared. So delta x is final position minus initial, since car 2 also start from x equal to 0. So the final position x2 is simply also somewhere here. So we say that final position for 2 minus it's this final position, okay? Minus initial is from origin. That's change of position for car 2. Initial velocity is 0 because this car is at rest right here. 0 and plus 1/2. Since this car 2 accelerates towards positive direction, so A is positive of what? 5.0. Time, we don't know how many seconds take it. So t, be careful, the t has to be squared because look at this equation. This equation, t is squared. So this is the final position of a car 2. We want it to equals to the final position car 1. So that's the equation. See, this means catch. So what we're going to do is we say, okay, final position car 2 can be expressed by this. That is 1/2 of 5.0 of t squared. Now take a look. Both sides equation have t. So this t and one of this t cancels. And then it looks like time t equals to 2 times 25. It will be 50 divided by 5.0. So it looks 10 of what? Time is in second because SI unit. So it takes 10 seconds that for the car 2 to catch car 1 because they are at the same location. Let's take a look at this. Not only answered this time and where we have answered this question. So that's pretty easy because in 10 seconds, where is car 1? So x1's position, since t equals 0 is right here, so it's 25 meters per second. After 10 seconds, times 10, it's constant speed. It's 250 meters away from the origin. That is where. But however, at that time, car 1 will still keep this constant speed or constant velocity, 25 meters per second. What will be car 2's velocity? Then we're going to use this equation. Say final velocity equals to initial velocity plus AT. For car 2, initial velocity is 0. Acceleration is positive 5.0 because it started to accelerate. Time is 10 seconds. So the final velocity for car 2 is 50 meters per second. Interesting. So after 10 seconds, 1 and 2, car 1 and 2 will be at the same location, which is 250 meters away from origin. Car 1 will still keep constant velocity 25 meters per second to the right, but car 2 already reached that 50 meters per second, travel really fast. Then what's next? Well, you get only a fraction of a second to talk to your friend because you travel so fast, you will pass him right away.